Today I'm going to present you the synthesis of silver tin oxide, silver zinc oxide, and silver zinc oxide tin oxide core shell nanoparticles by hydrothermal method. The authors of this project are Venkata, Khrisna, Karthik, Tangilara, Ismael, Posadas, Pichardo, and me, Yael Magaña Aguilar. Nowadays, improve the properties of materials is very important. For this reason, nanotechnology emerged as a possible solution to this problem. However, nanoparticles have some areas of opportunities. One of them, the lack of stability. To solve this challenge, the core shell structures were created because this favors nanoparticle stability for two main reasons: physical protection and preventing agglomeration. Likewise, creating a core shell structure allows us to obtain the properties and characteristics of two or more materials, which generates an improvement in future applications. In this work, we choose silver as a core because of its exceptional electrical and thermal conductivity. On the other hand, silver exhibits an optical phenomenon known as localized surface plasmon resonance, thus being able to generate hot electrons that can be transferred to the surrounding oxide layer, constituting a mechanism powerful to activate the layer and enhance its properties. We choose tin oxide and zinc oxide because they are widely studied and used for different applications, due to their electrical properties, high stability, among others. By combining these two metal oxides in the same layer, a heterojunction is formed at the interface. This junction acts as an energy barrier that greatly facilitates the separation of charge carrier, making electron holes translating to oxygen vacancies. Combination of that with the silver core is a triple action nanoparticle where silver amplifies the excitation of the layer and the layer's heterojunction maximizes the use of those charge carriers for a specific application. To characterize or materials, we employed various analytical techniques. For optical, dynamic light scattering, and Fourier transform infrared spectroscopy. For morphology, transmission electron microscopy and scanning electron microscopy, and for chemical, the energy-dispersive X-ray spectroscopy. For methodology, firstly a 0.01 molar solution of silver nitrate was prepared. Immediately 4.6 weight% of PPP was added. The solution was then heated at 70 degrees and stirred for 1.5 hours. Afterwards, the shell were prepared by taking 100 milliliters of the solution with the silver cores for each of the three different solutions. In the first solution, zinc chlorate was used as precursor. Zinc chlorate was used for the second solution, and an accumulated amount of zinc chlorate and tin chlorate was used for the third. All the solutions were prepared at 4.7 by 10⁻⁴ molar. Subsequently, the solutions were introduced into an autoclave at 160 degrees for 1.5 hours. Finally, the samples were dried at 100 degrees for 12 hours and 3 hours at 300 degrees. For results, the optical, then the DLS, represent a normal outward ripening growth with three characteristic groups. The first one in -10 nanometer, the second one in 450 nanometers, and the last one in 5500 nanometers. And the FTIR, the presence of different amino and carbon groups are shown in the graph, inferring a lack of calcination during the process. Also, the presence of the zinc-oxygen and tin-oxygen bond are in the graph corresponding to our samples. SEM shows for tin oxide samples circular morphology with average size of 150 nanometers. for zinc oxide samples nanorod morphologies with average thickness of 3.2 micrometers. Finally, for combining zinc and tin oxide sample, show the two morphologies. By combining these, we can obtain a sample with high active size from the circular morphology because the great area volume ratio, and good electron transfer from the rod because the rods make a good path for an electron, achieving improvements for applications such as gas sensing or photocatalytic applications. The theme confirms the presence of silver in all the samples. The darkest zones represent the silver because their higher atomic number of the element comparing to tin oxide or zinc oxide. Also, the tin oxide and zinc oxide are in the samples corresponding to the literature this type of structure as shown, and also the theme corresponding to a core shell structure because the darkest zones are into all this gray zone corresponding to the tin and zinc oxide. For chemical characterization, EDS shows the presence of zinc, tin, oxygen, and silver, corresponding to the core and shell chemical structures of the materials we made. Also, a higher amount of oxygen corresponding for the metal oxides and other compounds in the sample, as we see in the FTIR. Also, the third sample presents a similar amount of zinc and tin, represent for the synthesis we made, the methodology we use, and also in the same we saw the combination of the two morphology making sense that the amount of the zinc and tin are similar. This allows for an optimal formation of the heterojunction between the two metal oxides and the silver. To conclude, courses were successfully synthesized via hydrothermal method. The different morphologies found present a great area volume ratio which allowed for future application in gas sensing, electrolysis, photocatalysis, among others. For future research, it is proposed to increase the calcination temperature. Our references are in the QR in the bottom of the poster, and our mails are down of our names. Thanks for watching our work.